Hi, this is Neil from Xiaomi Villa team. Today I'm going to introduce you the memory debug tools and the GDB debug live demonstration. We already developed many debug tools. We will firstly have an overview of them, then focus on the memory tools. Finally, we will using the STM32 board to create a real crash and use the tools we learned to analyze it. And finally, we will use a GDB stub to actually debug the hardware. So why do we urgently need good debug tools? I will give you a real-world example. We have developed lots of wearable products. Most of them are based on Cortex-M microcontroller. They do not have MMU. For a large project, we normally need 3 major teams with more than 100 developers. So if anyone has developed a flaw in the code, it will lead to system crash immediately. So the importance for the debug tools is obvious because the code modules will affect each other. There is no isolation between them. Large team can increase the risk of flaws, so the stability is a real issue. With all the tools we have, is that really enough for the real project? The answer is never. We normally will combine several of the tools to debug a real issue. So here is an overview of what we have as of today. The first category is the static code analysis tools. There are free tools and non-free tools. These are really useful for a newly developed feature. The first thing we need to do is run a code check. And the tools are really useful because they will tell us exactly under what condition, for example, a memory leak will happen. The second category is the online debug tool. We connect to the hardware through Debug, for example, using the G-Link. We can also using the GDB stub, so we can connect to device using UART or TCP/IP. We use the GDB plugin, so we can inspect the thread information and switch between them. G-Link, we also added the thread awareness support. The third category is the offline debug tools. When a system is crashed, all we have is the crash log. So the first thing we need to do is to get the backtrace to where the code causes the CPU to crash. With the mini dump, we can pass a little piece of the crash log to reconstruct the situation of the code stack. We can inspect the variables on the stack directly. With the code dump, additional to the stack information, we can also dump the heap memory. So for the real hard issues to debug, the code dump is a good tool. The fourth category is the memory tools. It includes stack overflow detection, stack canary, and the memory dump tool that will help us to debug memory leak issues. We also have address sanitizer tools and Fortify. So next section, we will focus on the memory debug tools. So let's firstly understand how stack overflow will occur. Here is an example of the heap memory layout. There is a stack memory allocated for task A, and then there are other memories. If we declare a real large variable on task A, it will directly overflow to other area, causes a stack overflow. If the task A has a really deep code stack, because the code stack is really large, it needs lots of stack space. It can also cause stack overflow, especially when the call is recursive. The fourth situation is that we use a function to write to the stack buffer, and under some circumstances, the input parameter is wrong, which will cause the buffer overflow to a higher address. So how we could determine how much stack is really needed by the task? We can enable stack acceleration, which will write the whole stack with a magic number. There is a function will be used to check the deepest stack position. Hardware stack check is also available for some hardware. There is a register called MSP limit and PSP limit. When the task switches, we program this register, so when we use SP as a base point to access memory, if the memory is outer range of the stack position, it will let us know. There is also a stack check using R10 register can be enabled by ARM version 7 or 8 stack check. Basically, it will insert a function call to every function. This function will be called to check if the function will use a stack space larger than we have. Stack buffer overflow is a common case we will face. Stack canary is a tool that will help us to debug overflows to the higher address. Here is a typical stack layout for a function call. We will firstly push some registers to the stack, for example, the return address. Then we will define the local variables. For this function, we will copy some data to the buffer address. If we copy more than 16 bytes to the buffer, it will overflow to the canary word. By checking the canary word if it is changed or not, we will know if the overflow has happened or not. Stack canary can be enabled by this macro. Once enabled, all the functions will be added this kind of check. It will slow down the performance a bit, but not that much. Fortify is another great tool provided by compiler. It helps us to do runtime checks against the buffer overflow. Here is an example of the memory copy function after using Fortify. Our real memory copy will be called on the end, but before that, the parameter size, the parameter n, will be checked against the depth and the source object size. If we are going to copy more than the object size, it will assert directly. Currently, it covers most of the library functions. Fortify have different levels, and level 3 allows us to do heap check and stack check. Compared to Kson cannot do global variable check and stack check for now. Fortify also has a small impact on the firmware size and the performance, but it is limited to only check the library functions. Address sanitizer is also provided by compiler. Currently, it can only run on simulator, so it is useful for application development. The basic theory for address sanitizer is that the memory is marked as accessible or not on a shadow memory. So when memory access happened, the compiler will generate the code to check the shadow memory if it is allowed or not. Kernel address sanitizer, Kson, on the other hand, can run device directly. It can help us to detect out-of-bounds access to the heap memory or to the global variable. Currently, this feature is preparing for the PR. More importantly, it can help us to detect memory use after free, which is the downlink pointer. Without Kson, this issue is really hard to debug. Kson is a great tool, but it also has some limitations because every memory access instruction is checked. So the firmware size and the performance will degrade a lot. We can overcome this limitation by optionally disable the read check or the write check. Based on the theory we just mentioned, considering this scenario that we have two tasks, if task A allocated some memory and freed it, task B is going will also need some memory, so it will unlock from the heap. It can happen that task A released the memory and task B require that memory directly. So Kson mark that memory is accessible because task B will use it. But after some time, task A wants to use that memory directly because it's a use after free. Kson cannot detect this case because the memory is already marked as usable. So to overcome this limitation, we included a feature called memory delete free. So when task A releases the memory, we do not free the memory to the main heap directly. We insert the memory to a delete list, and when task B wants to alloc a new memory, it will alloc from the main heap. If the main heap doesn't have enough memory, then the delete list will be freed directly. So the system can run smoothly. With this feature added, when task B wants to use the memory it just released, Kson can detect this case. For the performance degradation and the firmware size increase, the hardware ASIN support is also added. In this section, we will talk about the memory dump function and the ECO memory leak and the memory corruption. So here is a typical memory structure. Beside from the essential manager info, we added a piece of statistic info, which includes information like where this memory is located, which is the backtrace to the function call, and what is the sequence number for this allocated memory. With this additional info, we can use command memory dump to dump all the system memories, and we can use free to check the heap memory usage. Memory backtrace can be enabled by this macro. When it's configured as -1, then it is disabled. The node overhead is only about the manager info, which is 8 bytes. When it is configured as 0, then it additionally includes PID of the owner of the node and the sequence number. When it is a positive number, it also includes backtrace to where the memory is allocated. With the help of memory dump, we can debug memory leak issues. So firstly, we need to determine if memory leak actually happened. We can do this by regularly call command free to see if the heap usage is increasing gradually. We can also enable scheduler dump leak, which will automatically dump the memory info that this task allocated but not freed. When the main memory is exhausted, we can enable dump on failure, which will automatically dump all the memory node info to the crash log. Besides from that, we can also use command memory dump to selectively dump memory info for the specified PID, for example, or for the user memory or the free memory. We can also specify the sequence number. Using tool pass memory dump, we can generate a report of the memory usage. For example, it includes the memory usage for every PID. It can also include the backtrace to the memory node. There is a trick to debug memory leak issue if we know for sure this scenario will generate memory leak. There are lots of threads running in the same time, so using memory dump directly will generate lots of memory node that is currently actually using, but not the leaked node. So here is an example that, for example, we have a UI that we enter this UI and leaves that UI, it will generate a leak memory. The trick is that before we enter this scenario, we firstly using memory dump command to check current sequence number. We remember this number and enter this scenario, and we do the normal operation, and finally we leave this scenario. And we check the sequence number again, we will see it is currently 1007. If we use memory dump command directly, all the red memory node will be dumped, so we cannot distinguish if the node is actually used or not. By specifying the PID to this scenario, so other threads will be excluded from the dump info, and specify the sequence number. So we will specify the 1000 to 1007. With this additional info, we dump the used memory. We will only have 1003. By checking the bytetrace to this node, we know where the memory is allocated, and then we debug why the logic to free this memory isn't executed. Besides from this trick, we can also use the leak sanitizer on the simulator. It's currently already supported. In the final section, let's talk about the JDB usage and get onto a real hardware. In this section, we will talk about minidump, calldump, and the JDB enhancement. Minidump is a useful tool that can be used when the system already crashed, but with useful logs. The log will normally look like this. It includes register value and the stack to the crashed thread. Using minidump server together with JDB tool, we can inspect the backtrace to where the system crashed. We can also switch to different frame and check the stack variable. Most of the crash will firstly use this tool. Here we create a crash by writing to a random address. Minidump works by copying out the crash log and paste to a test file so we can parse it later. So after JDB connects, we can switch to different frame and inspect the variables such as the pointer and the arguments. So the limitation for minidump is that it can only access to memories already in the stack. With JDB stub, we can connect to device that doesn't have JTAG. For example, we can use the UART interface. Here I have an example that runs on ST32 discovery board. So previously we already showed the demo using minidump. I'm going to using the same board, but I'm going to use the TTY USB, which connects to UART3 of the ST32 board. Using this command through the UART, we can connect to the hardware. JDB plugin is a Python script that allows us to access to program status and memory. We can, for example, execute command info threads to check all the threads runs under NAS. We can also develop custom code to, for example, go through the list. We can make the print from JDB much prettier. To use JDB stub, we firstly need to configure the baud rate for the device correctly and then use GDB to connect it. After connected, we can execute info threads and other commands to inspect the system. It uses just like a G-Link. After system has crashed, GDB stub allows the system stays there so we can connect to it later. After connected, we can inspect all the variables. GDB plugin allows us to inspect task information. It also provides other tools. When system crashed, the backtrace will show the interrupt backtrace. By using NuttX setRex, we can restore the user task registers so we can see clearly which command and which task has caused this crash. Compared to minidump, which only allows us to access memory stored to the crash log, which normally is the stack memory, calldump allows us to create a full snapshot of program's memory. It includes program's states such as memory content, processor registers, and stack trace. With the additional board memory range, it can also allow us to dump additional memory range to calldump. Calldump can be triggered automatically on when the board crashed or manually by command calldump. It will use the lib_erf function to generate file content using ERF format. The data can be then streamed to the backend, such as syslog and the file stream. It can also be streamed to block device directly. The data can be optionally compressed by RZF to further decrease the file size. To use calldump, we can firstly add a board memory range, so calldump will also dump this range of memory. We create a crash and the system will output the calldump data by syslog. We copy out the crash log and pass it to create a calldump file. Then we can use GDB tool to analyze it. We can also use the info threads command and check frame by frame. We can also inspect variables in the heap. This is all the short introduction to the debug tools I have today. If you have more questions, feel free to file a GitHub issue. Thank you.